Uh, Thomas Hill's flashback project later uh, ins- exemplifies this vision by using proof assistant Isabelle and whole light to verify his proof of the Kepler conjecture. This also demonstrates the power of formal proof to confirm complex results. And today's proof systems like Mizar, Isabelle, Cork, and Lean are invaluable for formal proofs, enabling precise verification and minimizing human error. Here is an example of a formal proof in Isabelle that shows the square root of 2 is irrational. And here we have a diagram illustrating theorem dependencies in Lean project generated automatically. We can see that large-scale proof analysis is a major advantage of using proof assistant. However, natural language math remains the most accessible format for both human mathematicians and AI models. We'll explain why formal math is also beneficial for AI research, particularly given a specific challenge of training language model in natural language math. Consider the METH or math dataset. That is a popular dataset and a standard benchmark for training and evaluating language models in natural language math. It is human readable and can be compiled from broad sources, with accuracy accessible based on whether the final answer matches the expected result after some normalization. The answer, for example, the answer of the solution is within this box. And we can see that this is simplicity in extraction, use, and evaluation. And this has contributed to its popularity. There are two main techniques of used to improve the AI performance in natural language math reasoning. First of all is the very famous chain of thought prompting. It encourages models to generate detailed natural language solution before arriving at the final answer. And the second is self-consistency method, which involves simply multiple solutions and determines the final answer by majority vote. Additionally, we can train a verified model to estimate the probability that a solution is correct. And we can use the majority voting among solutions ranked highest by the verified. And one challenge in training a verified model is the issue of false positives, where incorrect solutions might still yield the correct answer by flawed reasoning. Including such examples in the training data will misleading the model, impacting its ability to identify correct solutions during the testing of majority voting. And to address that, OpenAI and DeepMind have explored process supervised training with human annotations to identify reasoning errors in the training data. But this is human labor intensive. For example, the OpenAI's dataset, for example, requires over 800,000 feedbacks from human annotators. While outcome supervision is feasible with automatically trackable answers, automating process supervision in natural language math remains challenging. This is where proof assistants offer a potential edge in supervised learning for AI in mathematics. More importantly, in a formal system, the correctness of a theorem proof can be verified, not just confirming whether the answer to a computational problem is correct. Theorem proof is the main content of mathematical knowledge, while problem solving is just exercises and examples. Process feedback of theorem proving in formal system work like this. For example, giving a specific hypothesis before the V-dash symbol and the ghost after the V-dash symbols. This constitute a so-called proof state or tactic state in Lean language or and other tactic-based proof assistants. And then we input one of the commands that calls tactics into it, and the proof system will validate this tactics, the tactics application. If the step is valid, the proof will proceed, and the next state will be feedback by the proof system. If this tactic application contains errors, then this error is flagged to ensuring the accurate feedback. So, how advanced is the best AI for formal mathematics today? It is Deepmine's AlphaProof. It achieved a silver medal in 2024 International Mathematical Olympiad and was just 1 point away from the gold medal. However, it is closed and closed-sourced, so details and direct access are limited. For the open-sourced models, benchmarks are essential for tracking process. The mini F2F benchmark evaluates AI on high school level problems, including some IO questions. And our DeepSeek-Prover version 1 achieved the state-of-the-art result in this year, and surpassing the long-lasting record of Meta's HTTPS established at 2022. And furthermore, DeepSeek-Prover version 1.5 further improved its performance. And ProofNet is a more recent benchmark assessing undergraduate level problems across areas like analysis, algebra, linear algebra, and including linear algebra and abstract algebra and general topologies. And we also achieved a substantial improvement on this benchmark as well. Now, let's explore the methodology behind the DeepSeek-Prover. First question is that, how does our model prove theorems? It is that just like the AlphaGo, our approach relies on Monte Carlo tree search with our novel truncate and resume mechanism. First step A is for example, the step A, we used a tree policy and select a node and retrieve its proof code so far. Includes the handler, the initial statement, and the previous tactics that is successfully applied within the previous tree expand. And step B is that the language model will generate the next proof steps after receiving the current tactic state that from proof assistant. And step C is that the proof assistant will verify the completed proof. If no errors arise, then a valid proof is found, and the tree search terminates. If errors appear, we truncate the new code as the first error, and discuss the rest and use the successful new generated tactics to expand this search tree. And step D, we repeat this process until a proof is found or time runs out. A valid and And a valid and a complete proof trajectory is a series of actions and states that lead from the initial statement to a proven a conclusion. A trajectory is only valid if each of the actions application is validly advanced as a proof and complete, and it is complete if all proof goals are met. Each proof stage starts from the from the root node and move downward, with nodes selected based on the tree policy. The tree policy is to maximize the state action value or so-called the Q function through this procedure. And this procedure will choose we choose to expand this node S itself, or we choose to expand or we choose to apply this tree policy, continue to move on to one of its children. This procedure enables efficient navigation through proof states to choose the most promising code prefix for further exploration. The tactics action value or Q function is computed using the standard upper confidence bound algorithm with some modification. It is to balance the exploration of new states and also with the exploiting known reward signals. However, the sparse reward present a challenge. A natural reward design is to assign positive reward to only valid and complete trajectories, but we obtain this positive reward only when a proof is found, and then the proof search is terminated. In other words, it means that during any proof search procedure, we will have no positive reward at all. And if we obtain a positive reward, then the whole proof search procedure will terminate and cannot provide any positive or useful information for further exploration. And to tackle this, we introduce the intrinsic reward for novel state expansions to encourage the model to explore new proof states. It means that for all states, we consider the trajectory that have visited it. The tau here means the trajectory. If states have more trajectories that this trajectory have been lead to other novel states, then we assign higher chance to continue to expand from this state, and this fills the R function in the original computation of the state action value or Q function. Therefore, we want to encourage the further exploration of new states until a valid and complete trajectory is identified, or in other words, the proof of the original theorem is found. Then another question is that where does the training data come from? Indeed, proof system language, contrasting to the other popular programming language, for example, the C++ and Python, they are used by relatively few experts and result in limited dataset. To train the DeepSeek-Prover, we synthesize the formal mass data through the so-called autoformalization. Autoformalization means that we translate the proof of a statement or even a proof from a natural language problem to a formal theorem statement, and in this pipeline we convert the informal math problem into formal statement And finally, we generated 8 million proof of for training. It is this process is complex as the language model can produce inaccurate the translation of informal problems into statements and or even caused inconsistent hypotheses. But sometimes, for example, if the formal statement contains inconsistent hypotheses, then we can derive any conclusion from it very trivially, and this are many difficulties to during this generating of high quality data set and detail and other and also for example the model may generate a false statement. That is, we can never successfully prove it, but its negation may be provable. And we use a symmetric procedure to decide this truth value. For example, we parallelly try to prove itself and its negation. And if one of it is successfully proved, then we have decided the truth value of this statement, and we gather the no matter the proof of the original statement or the proof of the negative statement as a proof in the training data set of our model, and we use all of this data set to train our model to enhance its capabilities in both proven statement or proven negation of a theorem. And all of these details are in the DeepSeek-Prover version 1 paper.
Can I ask a question about the previous slide?
Sorry.
Can I ask
Please.
Can I ask a question about the previous slide?
Okay.
So in your informal math problems that you gathered, do you like, for example, your test set mini F to F contains a lot of standard problems from, like, for example, it contains AIME 1994 problem 3. Do you remove those from your scrape problems, or are those part of the scrape problems, and then you don't scrape the proofs, but you just have more time to actually work on that problem than just at test time?
Indeed, we have used some very simple techniques to remove the exactly match problem from the informal math problems that we scrapped from the internet. And we also consider the so-called potentially the data leakage problem. And indeed, this there are only first of thing is that there are only very few chances of to extract exactly the same problem from the website. And the second that we do such techniques to remove these exact match problems. Yes, and I think this has been appropriately done.
Okay. My other question is, with the auto formalization, like, you have kind of a feedback loop here. Do you do anything to train or modify the formalizer given feedback from, like, which formalizations are correct or which ones have errors, or is that a fixed component that you just leave throughout the whole system?
Yes, this is a very good question. And indeed, we use a very simple technique that if this formalized statement it has been successfully proved, no matter or the negative statement, if it is proved, if the original statement is proved, then the pair of the informal math problems and the corresponding translated formal statements, this pair is used to train our model to enhance its auto-formalization capabilities. That is, we decide whether a data set, the data of auto-formalization data pair is good or of high quality, is that it is provable. Right. And also, indeed, there are also other methods, for example, the so-called model scoring, that the model takes some consideration to decide whether this is a correct auto-formalization. And indeed, the most stressing thing is provability. Yes.
So I understand you have this way to score things, and I think maybe I'll talk about that later. But do you do you change the formalizer at all? Like, do you fine tune it on the correct formalizations or use those in the prompt, or do you just leave like that the same throughout the whole thing?
Yes, indeed, the autoformalization model and the theorem proving model and all other model are all the same model that we use the same checkpoint to do all these different tasks. And the training data set of this single model is composed of several multitask purpose. For example, we mix the autoformalization dataset and the theorem proving dataset and in a single training dataset to train our single model. It means that each time we gather the newly generated theorem prover system and the corresponding the proven data pair of autoformalization uh, together to train this model. Therefore, the capabilities of autoformalization or theorem proving are intended to enhance together. Is it
So you
clear?
use the same model for auto formalization
Yes.
and theorem proving, and you use this data to train both parts of that model. Um,
Yes.
okay, thanks.
Thanks. Thanks. Thanks for your
Hi,
question.
Shismi, can you hear me? I have a question.
Please, I can hear you.
Yeah, thank you. So in the auto formalization process, let's say you have a problem in natural language that needs you to prove a statement about complex numbers, but then let's say your formalizer makes a mistake, which just forgets to include that condition it's over complex numbers. So maybe it produces a wrong statement that only that's only about real numbers. But then about real numbers, it's trivially true. So in that case, you do get a statement that you can prove, but that statement is not very meaningful. Do you take any measure to prevent this?
It is a very good question, and this current case is difficult to measure and to escape. And indeed, the solely techniques that we used in this paper is so-called model scoring. But as you understand that whether the statement corresponding to original informal math problem is hard to decide, even for a very large model, for example, the GPT-4o. And we used only a 7 billion parameters model. And there must be many cases that is too over simplified. Yes, this is a very good question, and currently we haven't got a very perfect solution to this question. Maybe but currently I'm also focused on this problem, and I'm trying to propose some more complex scoring method to solve this problem. Thanks.
Thank you.
Thank you. Okay, let's move on. For the collected proof data, we used a large general model. Indeed, it is a DeepSeek-Prover 236 billion parameters model to translate the formal proof into the natural language steps one by one. For example, first of all, we try to translate each of this title application into a corresponding natural language explanation, and we place it before the as a comment before this title application. And after all, we try to translate the whole idea behind this formal proof into a complete natural language solution, and we place it as a multi-line comment as an initial part of this proving part. And after we compress this kind of data set, we use this formal proof with corresponding natural language explanation to train our model. And we found that, and this case is indeed a real case that is generated by the final model, the DeepSeek-Prover version 1.5. And it has successfully and reasonably, first of all, trying to conduct somehow natural language reasoning, and then to transfer it to a formal proof that is verifiable by the Pro assistant. And we found that for some very complex problems, it can indeed to enhance the performance of theorem proving. And the next question is that how is our model trained on this synthetic data? Indeed, our training procedures follow the all standard large language model training techniques, involving 3 stages: pre-training, supervised fine-tuning, and reinforcement learning. And I want to stress the reinforcement learning stage is that giving an incomplete formal proof and the ground truth tally state from the proof assistant. Then we roll out the language model to generate several different completion to this proof, and we use it to verify with proof assistant and to decide whether the proof is correct. And the correctness constitutes the binary reward to the reinforcement learning procedure. And what should further stress is that different traditional application of reinforcement learning in theorem proving tasks. That is, most of them is tree search, and each step is generates one net statistics and evaluate and to expand further. And we proposed the reinforcement learning procedure in this tree search style as they done in AlphaGo series. And in our use of reinforcement learning, indeed we do not use a tree search, right? And we just that we use the reinforcement learning of that is so-called reinforcement learning with human feedback, and we take it as a whole sequence generation problem, and use the standard techniques that use in the LHF techniques. And indeed, this is very effective, very fast, and we can iterate very quickly. And this comes from the benefits that we use the whole proof generation, that each time we can just simply the model to generate the following all trajectory till the end. And this is similar to the so-called simulation process that is used on the MCTS of AlphaGo 0. And indeed, the sampling or simulation process is quite straightforward, and we can achieve a quite good performance with very few simple budget. And later we will revisit this issue. And and in my opinion, this is a key that our reinforcement learning can work, right? And this is an evaluation matrix that indicates consistent improvement across the training stage. And what should be stressed today is that it showcased the excellent test time scaling. It means that the performance would steadily improve as the sample budget increased. And yes, it is a very popular name, so-called test time scaling. But so to some extent, we have demonstrated this similar phenomena in this work. And finally, how effective is our resulting model? And in this, there is a simple version of comparison of various theorem proving method on the mini F2F benchmark. And DeepSeek-Prover version 1.5 achieved 33.5% and performing other state-of-art method and details and the complete version of this form can be found as this paper. And as for the provenance benchmark, and the DeepSeek-Prover version 1.5 also leads a good score of 25.3%, significantly ahead of other previous approaches. And as we previously mentioned that another advantage of our model is that it is efficiency under a small, simple budget setting. For instance, we achieved the equivalent of previous models' performance with only 30 samples, while our 3,000 sample performance exceeds the previous model using 200 of thousands samples. Indeed, this is not a very why should I mention this? Is that it is very useful not to achieve a new state-of-art result in the benchmark, and but for example, the data synthesizing procedure that we want to firstly decide whether a statement is correct, as I mentioned before, and if we can decide this problem with only tens or hundreds of times of generating, and indeed this generation procedure can be parallelized with so-called, for example, the VLLM and other infra. And then we can very efficiently to scale up the data synthesizing procedure, right? And if we require large-scale heavy tree search procedure, and we may be required to generate multiple samples to solve one problem that it maybe requires, for example, 6 steps of 6 tactic to solve a problem. And and in traditional tree search procedure, you need to apply the model 6 times. And in the whole generation setting, we can try to generate them with one time. Although it's not a very fair comparison, but I still think it is useful for some purpose. And finally, we
Sorry, so for that last one, what was a sample? Well, a sample is just a number of times you call the model?
Yeah, the number calling the model. I also mentioned that it's an unfair comparison because, for example, the output length may be different, right?
Okay.
Right.
Is this like how many independent tree searches is this 3,200 number?
There is no tree search in this version. This is very simple the whole generation setting.
Oh, this is okay, just independent samples.
Yes, this is independent.
Oh, okay.
Yes, and in my usage experience, this setting is very useful, and because it is really simple. Finally, we arrive at the conclusion, and today we have discussed why formal mathematics and AI can be advanced together, and examined DeepSeek-Prover's method and the results. And finally, we summarize the main takeaways. First of all, formal theorem proving ensure rigorous verification in mathematics and provide an accurate, reliable framework of AI, and is much more cheaper than the procedure supervision with a human annotator. And the DeepSeek-Prover series excel through exploring novel states, synthesizing data, and reinforcement learning with proven system feedback. This component contributes to a more robust language model for theorem proving, as we see in the evaluation state. And Thank you for attending today's presentation. If you have if you'd like to have more information, please visit our project page or feel free to reach out me. And I look forward to any question. Thanks.
Hi, I have a question. Can you hear me?
Yeah, I can hear you. Thanks.
Okay, thank you. I have a question about the data generation part. So I remember in your paper, you mentioned that you have originally like 1 million problem, which is the formal statement. And there is another technique that turns this 1 million data into 8 million data. So how is that technique like?
Indeed, this is not a very complex technique. Indeed, this we just, for example, for one formal statement, we can generate various proof of it, and all of this is correct, right? For example, we can apply
How
different
did you
techniques.
yeah, how did you generate that variance?
For example, we we try to prove a theorem with, for example, 100 and even 1 million times. Then there may be some attempts the model will generate all of them correct proof, but they are different with different idea, different application of tactics, and different style. Is it clear?
Okay, so the problem statement are all the same, but the solution paths are different.
Yes. At this stage,
Okay,
we haven't done for example, the data augmentation, for example, the modify some hypothesis and transfer to another form. We haven't do this. We use
oh,
very
you didn't do
straightforward.
that. Okay, okay.
Techniques.
So in Alpha Proof blog, they mentioned a technique called like a problem variant generation, which turns the like 1 million data into 800 million data. So do you have any comments on that?
Yes, I think this is a very important and common techniques that is used to inform to augmentate training data. And indeed, not the DeepSeek-Prover series. There has been another paper that previous done by me. It's called Lego Prover. LEGO prover. And in this paper, we explored some techniques to so-called self-evolving that we modify some items of a statement and to transfer to another form. For example, for a very simple problem in natural numbers, we can transfer it to a real number problem. And other, for example, another very in our mind is very simple techniques to generate a variant or a variant form of a theorem. But I think this is a area that have not been fully explored. It means that there have not systematically method to generate a meaningful variant form of one statement. I think I'm looking forward to the research in this area. Thanks.
Thank you.
Hi, I have a question. Can you hear me? Yeah.
Yeah, I can hear you.
Okay, thanks. So I had a question about the Monte Carlo part. And specifically, I know like at that, when using Monte Carlo methods, the number of iterations per second you can go through is pretty important for the learning to be effective. So my question is, do you feel like you ever ran into any limitations due to the performance of Lean itself? Because I know, with dependently typed languages, type checking or proof checking can involve a lot of like unification. Like sometimes it's pretty slow. Do you think for what you've done, has that been a bottleneck so far or not?
Indeed, we just use we do not spend much time on optimizing the foundational infra of Lean verification, and we just straightforward to use to the standard REPL the tool by Kim. And indeed, we really feel that the Lean verification is quite slow. And indeed, this is one of the bottleneck in our scaling plan. And I heard that in the paper in the blog of DeepMind, they have done very good optimization of Lean verification infra. And I think indeed I'm very looking forward to the optimization open source tools of Lean. Yes.
Okay. Cool. Yeah. So one thing, I don't know, you probably already thought about it, but just in case, is you know, when you had those examples of the natural language comments in your proofs, if you like took those and turned them more into like formal like Lean level intermediate steps, then that would reduce the amount of unification that Lean needs to do, which would make the proof checking like very fast. Yeah, like here, like this, you know, since a plus m plus c equals 12, like you could like break down the proofs into smaller pieces so that Lean unification needs to do less work. Yeah, that's typically I don't know what I would do if I wanted type checking to go faster for this kind of thing.
Yes, it's a very good question. And indeed, what I consider is that there is one thing to be balanced. Is that if we use the very specific application of tactics, that instead of the very complex tactic, for example, the omega and so norm number SOP, and we use the very clear apply and rewrite command. It really makes this pro checking more faster. But it also make this precision proving problem is more difficult for language model. It means that sometimes the model don't have very clear idea to how to solve this question, but we can rely on the automatic tactics in Lean to tackle it. And if we use very specific application of tactic, then maybe we will spend more time in the sampling or generation of language model, and vice versa. And there may be intermediate solution. For example, we can have automatically we can have automated tools to transfer very complex high level tactic into some very simple application. Yes, and I'd love to see that.
Yeah, no, that makes sense. There another like intermediate thing would be like, even if you keep the proof the same, like omega, you can still break it down into a series of, let's say, 3 term rewriting equivalences, and omega proves those all trivially, but at least it will help the Lean type checker to go faster because it knows the pieces that it doesn't need to do unification, basically. Anyway,
Yes,
I'd be happy to talk more about it if you're interested, but yeah.
yes,
Thanks.
I also think it's very interesting. I'd like to also to mention that it is this even more complex problem when we compare Lean with Isabelle, for example. In Isabelle, we have very good automation of tactics. For example, the sledgehammer of auto and other that. Sometimes they use even longer time to solve goal. But it is very easy to use, and usually the performance of language model on Isabelle will be much more higher than in Lean. And this is a reason that many researchers would rather to work in Isabelle. Yes, and indeed, I think there are many considerations that should be balanced. And I think it indeed really area that was further exploration. Thanks.
I have a question about your tree search. So if you like go back to the first slide where you were showing the tree search, yeah, I guess even further back you had one. I don't know if it matters. Yeah, that one. So it's not quite clear to me what you're branching on. So so you first try to generate a whole correct proof, and then if that fails, you start branching and doing a tree search. Is that correct?
Yes, you can understand as every time we, instead of generate the next one tactic, we generate the next a sequence or chain of tactics. And indeed, when generating, we use it as a whole, so-called whole proof generation. Indeed, it is a multi-step prediction, right? And in the tree modification or tree update, we pass this newly generated code into isolated tactics, and each tactic is corresponding one node in this tree. And after parsing and tree update, this situation is very similar with the traditional method to perform a tree search.
So I mean, so when you backtrack, or it's not backtracking, it's Monte Carlo tree search, but like when you branch, do you only branch on tactics that failed, or do you just kind of, or can you branch on any tactics? Because sometimes a higher up tactic can cause a lower tactic to fail.
Indeed, as I illustrated here, if a tactic is failed, then we discard all of them. That is, the failed tactics will not occur in this search tree. And every time we expand from a successfully applied tactic and continue, for example, we have successfully applied this tactic and we have a new state. And then if we decide to decide with the tree policy from this state, we continue to generate from this state and generate following tactics applications. Is it clear? Sorry.
So say it again. So you said from this state you continue. Like, what is this state? What is the state you determine? How do you determine the state that you start to generate from?
Okay, it is a state I mentioned here is exactly the tactic state, right? I mean that after applying a linear sequence of tactics, we will arrive at a tactic state.
Well,
And
okay, you have lots of tactic states, right? You apply a linear sequence, and then for each
yes,
tactic, you have a tactic state, and so there's an error somewhere in the proof, and then you're going to start branching. You're going to start doing tree search, and
okay. Maybe I'll understand your question that the tracing of proof is linear, and we take it as a sequence generation or completion problem. And the branching is only occurs when there has been multiple alternatives tactic application to one single state. Then there is a branching. And if
so do you always start at the top and just start having the language model generate again, and then you've noticed like here's where the proof diverges?
I try to understand this question that maybe you mentioned that for example, if we after applying tactics, we have a tactic state composed of, for example, two cases. And in the traditional techniques, we take it as a branch from one node to corresponding two nodes.
Yeah.
Is it? Yes. Indeed, we do not difference these two nodes, and we take it as one single node of one tactic state consisting of two cases, and each have its hypothesis and goal. And this is how we done for human coder in using Lean, right? For example, the Lean every time when we write the next ticket, the Lean compiler will by default apply it to the first case in the steady state, and we follow this rule, and in the so-called we can take this the maybe there will be branching the tree of proof and flatten it into a sequence, and we take it as a sequence instead of a tree.
I mean, I guess I understand the proof you can think of as a sequence, but so like in a lot of papers, you think of a proof as a linear sequence. You think of each you have each state of your proof, and then your actions are individual tactics that get you to the next state of the proof. And
Yes.
and then once you have that, you can start thinking of branching, where you have you can from each state you can go to different, you can do different tactics. But I guess what is different is you're generating multiple tactics at the same time. So but is your action still individual tactics, like in the sense of the Monte Carlo tree search? Are those actions individual tactics, or are those actions like generating another proof based on a previous proof?
For example, after applying the constructor, we will have a steady state of two cases, right? And indeed, we continue to generate the following tactics, and the first few will apply to the first case, and the later few tactics will apply to the second case, right? And
Yeah.
all of them is generated linear or sequentially by the model, and that model then we may consider that the model are required to consider when the first case has been solved by the first few tactic, and then we move on to the second case, and also applying several of them to this case. And we take this order of cases as also corresponding the order of corresponding proof steps attached to it. We don't take this branch.
Okay, I think I just need to read the paper again. I think I'm confused, but thanks.
Sorry for confusing. Sorry.
Okay. Thank you for the talk and all the great questions. And if you have further questions, let's keep it offline, and let us thank again for our speaker. Thank to our speaker, Huajian, for today.
Thanks.
Yeah. Okay. Bye.
Bye.